Yeah, hi, thank you. This is kind of an unsatisfying talk because I don't really understand anything yet. But that's okay because I only have about 18 minutes, so I just thought I would use this to sort of collect some observations and simulations, a lot of it by other people, some of it involving me. And maybe you can help me understand what's going on. I'm particularly interested in the patterns that emerge on large scales in turbulent or strongly forced thermal convection. So this is not like the weakly supercritical regime in which a lot of pattern formation studies have been done. So I'm just thinking of ordinary Rayleigh-Bénard convection. If anyone doesn't know, that's just a layer of fluid where you in some way are driving heat upward through the fluid. This is typically modeled using the Boussinesq equations, which are written here in dimensional form. You have an incompressible velocity field U, and then you have your temperature field, which creates a upward in the upward z direction. It creates a buoyancy force that is proportional to the temperature, right? Because if something gets warmer, it becomes less dense. It wants to rise upward. I have to consider at least two different thermal boundary conditions here. So the two most common thermal boundary conditions would be that you drive the system with fixed boundary temperatures. That's what you see on the left. So you would fix the top to, let's say, a temperature of 0, and you fix the bottom to a strictly larger temperature of delta. The second most common way to drive this system would be to fix the boundary fluxes. So that would be the same as setting the vertical gradient of temperature to some negative beta. If you want to, say, non-dimensionalize this system, you can scale length by the height of the layer, which I'm going to do, so I'm always going to be talking about the height of the layer as 1. You can choose, for example, the thermal diffusion constant kappa to non-dimensionalize time. For a temperature scale, on the left you can use the temperature difference between the boundaries, but on the right you would have to take the layer height h times the gradient beta. In either case, you end up with PDEs non-dimensionalized that look the same. You have two dimensionless control parameters, the Prandtl number and this control parameter r, which you might like to think of as the Rayleigh number. Although only in the left-hand case does this Rayleigh number coincide with the most standard definition. And on the right, it's a little different because your temperature scale was h times beta. I also have to think about different velocity boundary conditions, in particular no-slip conditions where the velocity goes to 0 at the boundary, or free slip conditions where the fluid can slip freely against the boundary. Okay, now if you do a simulation of this system with relatively strong thermal forcing, here the Rayleigh number is 10 to the 8, and if your domain is not so big, you'll find that the flow organizes itself so that this is a temperature field, so that the warm fluid that's rising kind of coalesces so that it's rising in roughly the same place, and then the cold fluid that's falling kind of finds its own region. All right, but the question is, what happens when you make this domain large in the sense of having a much larger horizontal extent than the vertical distance of 1? So this was investigated in a pair of papers from 2004 and 2008 by these authors. So here we're looking from above at a somewhat larger domain. So this is a 2 pi by 2 pi in the horizontal direction. The height is 1. And we're looking at a temperature slice from above. So the hot red fluid is rising towards us and the cold blue fluid is falling away from us. Now you can see that the flow has kind of organized itself so that the distance between the rising and falling regions is about order 1. If you now leave this for a very long time, you find that actually what happens, or these authors found, is that the rising warm regions coalesce more and more, come closer together until you have one connected region of warm rising fluid and a connected region of cold falling fluid. It was not clear in this first paper whether this would continue to be the case as you made the domain larger and larger. Right? So in the next paper, these same authors,
condition horizontally.
periodic in this case, these same authors just considered a bigger domain. So now both horizontal directions are 6 pi times larger than the height of the layer. And what they found is, in fact, the structures do saturate at a certain scale. That's 2 or 3 times the height of the layer. And this is basically the same scale of saturation at 3 different Rayleigh numbers. I need to point out this is with fixed temperature, no slip boundary conditions. This will be very important. Then, in this paper from 2021, and a follow-up from this year, these other authors did this in an even larger domain, where the horizontal extent in both directions is 60 times the height of the layer. And they also considered various combinations of boundary conditions, and they found something that, to me, was quite surprising. So this is their picture for the exact same boundary conditions as the earlier papers. This is a slice near the cold boundary layer, so the fluid is all relatively cold. But hopefully you can discern that there's, again, a kind of characteristic scale in which all this overturning motion is organizing itself. That's, again, it's order 1, let's say. It's 2 or 3 times the height of the layer. Now, if we keep the fixed temperature boundary conditions, but we make the velocity boundary conditions stress-free, these authors found essentially the same picture. This is after waiting a very long time until the selected scale reaches some statistically stationary state. If it's a little bit larger scale, and if you zoom in, you don't have as much fine structure because the boundaries sort of don't stir the fluid up as much when you have stress-free boundaries. The surprising thing is what happens when you switch the thermal boundary conditions. Rather than fixing the temperature, you fix the heat flux through the layer. Now, these authors ran the simulation, and they wait a very, very, very long time, relatively speaking. And this is what they found. They found that eventually you get a domain-filling structure where all the hot rising fluid has coalesced, and it takes a long time for this to aggregate. So you get this domain-filling superstructure just from changing the thermal boundary conditions. Now, this surprised me because this is a no-slip boundary condition, so there is resistance to the large horizontal circulations that you would need in order for all the rising hot fluid to go way across the layer and become the falling cold fluid. Nonetheless, this is what they found.
David, is that a slice near the bottom again, or is that at mid-depth?
I forget. But, yeah, sorry, I don't remember.
What about the Rayleigh number?
So the Rayleigh number, I haven't written them because they found this at various Rayleigh numbers and various Prandtl numbers, going up to a Rayleigh number of about 10 to the 8. There is no indication that this, in 3D, that this depends on the Rayleigh or Prandtl number. So here's the same experiment with fixed flux boundaries, free slip boundaries. You again find a domain-filling superstructure where this domain is 60 times wider than it is tall. And yeah, so they found this exact same thing at all combinations of the Rayleigh and Prandtl number that they investigated. In the first paper, they only varied the Rayleigh number. In this 2024 follow-up, the first author varied the Prandtl number over a wide range. So this is kind of a neat and tidy story, at least in 3D. So the obvious question is, why do these really large superstructures form when you have fixed flux boundary conditions? I don't have a good answer for this. I don't have time to explain some sort of partial answers that have been suggested, but the reason I really don't think anyone understands this is because I've never seen an explanation of why 2D is different. So one thing I should point out, you may know that in the linear stability analysis of Rayleigh-Bénard convection, if the Rayleigh number is small, the conductive state is stable. As you raise the Rayleigh number, eventually the conductive state goes unstable, and in the fixed flux case, where you get these large superstructures, the most unstable mode is of domain-filling scale. So that sort of sounds like it might explain this, right? And in fact, you can take this into a weakly supercritical regime and do asymptotics, which is what Chapman and Proctor did in 2D, and said, you know, if you have fixed flux boundary conditions, even if you have multiple steady solutions to the PDEs, the one that's stable will be the one with the widest domain filling structure. This by itself doesn't necessarily explain what's happening in the turbulent regime, right? And this is particularly true in light of what I'm about to tell you in 2D. First of all, Chapman and Proctor's analysis is in 2D, but it's not consistent with what you would find in simulations in 2D. Okay, so first of all, let me back up and say, if you fix the parameters in the geometry, do the superstructures even select a unique scale, or can the state that you eventually end up with depend on the initial conditions? In 3D, a sufficiently large Rayleigh number, the answer is maybe yes. It does usually seem like there's a single turbulent attracting state. Maybe it can sort of lock into different patterns, but if you wait infinitely long, I'm not aware of evidence that there are states, where you'll end up with completely different quantitative properties if you take, for example, infinite time averages. In 2D, however, there's definitely not a unique selected scale. There's strong evidence in 2D that there are multiple locally attracting states, and what initial condition you start with will determine what scale you end up with in the end. So in 2D, convection looks more like this. You'll lock into patterns of convection rolls, which on average are the same size. However, how many convection rolls you end up with totally depends on your initial condition. So this was studied systematically in these two papers by Chi Wang and others from 2020. These are the same boundary conditions that I showed you initially, fixed temperature, no slip. Here they start with a certain initial condition that has a certain dominant horizontal scale, and they run for a long time, and you end up with a state that seems to have locked into 6 pairs of convection rolls. There's no indication that that will ever change. On the other hand, you simply choose a different initial condition with a different dominant horizontal scale, and you lock into a state with 4 pairs of convection rolls. Right? The only thing different is the initial conditions. If you keep the fixed temperature, so the thing that will not give you large scales in 3D, but you have stress-free boundary conditions, well, suddenly you have the same kind of situation, except the rolls that you can find can be extremely wide. These aren't really that wide. This is a pair of 2 rolls in the bottom picture. These authors find this exact same thing, a pair of 2 super wide rolls in a domain that is 128 times the height of the layer. Stress-free, but not fixed flux. Right? So those authors summarize this by saying, on the left, in the fixed temperature, no slip case, you can get different roll sizes to sort of lock in, but they're all order 1. On the other hand, fixed temperature free slip, you can, it seems, get a domain filling pair of rolls. So, yes?
In the simulation, it looked as though you were getting these little plumes that were building secondary structures on the main plumes. So maybe you just haven't gone to a large enough roll size.
You think if you went even larger, you might not be able to find
Those
them?
little plumes might develop enough to break up the...
Yeah, so let me address that at the end, hopefully. So let me summarize what I told you so far. None of this is work that I am involved with. In 3D, where the selected scale might be unique, right? With fixed temperature, you have order 1 structures. With fixed flux, you have domain filling structures, at least up to the size of domain that has been studied. In 2D, where you have a range of selected scales possible, with fixed temperature, what you can get depends on the velocity boundary conditions. With fixed flux, well, that data was not available. I particularly was wondering what would happen in the fixed flux no slip case, because in 3D, that's where you can get this large structure despite having no slip boundary conditions. So I had my master's student, Matthew Lewis, look at this. So 2D fixed flux, no slip. The question is, can you find these wide domain filling roll structures, or would they break up, as Neil suggests might happen? He just fixed the domain size to 20 times the height of the layer. We don't even do what Chi Wang did, where we try to find every possible roll size you can find. We just want to see if we can find this state. But we look for it very carefully. Like once we find one, we'll slowly, continuously vary the parameters as we continue to integrate to really try to map out where in the Rayleigh-Prandtl plane you could find such states. And here is one picture summarizing a year of Matthew's work, which is basically saying everywhere there's a circle, Yeah, we could find a domain filling structure in 2D with these boundary conditions. The X's indicate places where we could not find these states. It's not so clear. They typically break up into 4-roll states, but you have some weird metastability stuff. So you can't really define the boundary exactly. But essentially, you notice that as the Rayleigh number becomes large, this is about 10 to the 6, these domain filling structures go away. So 2D is totally different than 3D. And that's why I don't really think any of the proposed explanations could really tell us why what happens in 3D with fixed flux boundary conditions happens. Okay, so let me just summarize that by saying, well, I think here at large Rayleigh, you're order 1. And I can't comment yet on the other question mark case. So some questions that this raises are, why do the thermal boundary conditions control the scale selection in 3D? But at the same time, why is the velocity boundary condition more relevant in 2D than it is in 3D? And these domain filling cases, do they in fact saturate at finite scales? If you made these domains huge, 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 might it be that you don't get a domain filling structure? In 3D, I think it's really hard to predict. In 2D, contrary to what you maybe suggest, Neil, I kind of think you can get the rolls as wide as you want. Right? The reason for that is that there exists another type of state that you can find in 2D if you have free slip boundaries. So in addition to the sort of ordinary roll state, if you have horizontally periodic domain, you can also, for just a different initial condition, find a state that looks like the one on the bottom. Right? So you might think how could you have an infinite or arbitrarily wide roll if it's just driven by these 2 thermal plumes at the ends? It would have to break up. But what happens is that when a roll gets really wide, there's sort of something sneaking through in the middle that's actually sustaining this through Reynolds stresses. So the question then is, is this bottom state, what I like to call windy convection, is this in a quantitative sense a limit of an infinitely wide convection roll? Well, that's tempting to think, but actually it's not clear that this state on the bottom is in fact truly a stable state. And that turns out to be a hard question. You can run this bottom simulation as long as you like, and if the Rayleigh number is large, it will never go away. But once you try to actually say, if the Rayleigh number is small, it will go away. The bottom state will break up and you'll get 2 rolls instead. So if you try to say at what Rayleigh number does this become sustained, it becomes a little murky. So this is a paper we did last year that was doing a bunch of simulations at a parameter regime where you get this windy convection for a long time and then it suddenly goes away. And you can create a whole ensemble of these simulations and you get these spontaneous transitions and then you say, how long did it take to transition? We've already heard this kind of study spoken about yesterday. Right? And you find that the fraction of things surviving decays exponentially in time, so it behaves as a memoryless random process. But the Rayleigh number, as you increase it, these things live longer and longer, and you can look at the mean lifetimes. And then you would say, how does the mean lifetime depend on the Rayleigh number? Is the lifetime becoming infinite at a finite Rayleigh number? Well, the answer is we have no indication that these windy states actually become permanent, stable, right? Because here I'm showing the mean lifetime of these ensembles as a function of the Rayleigh number, and there's no indication of it reaching infinity at a finite parameter value. Instead, it's growing like a power law. It's growing like Rayleigh to the 4, roughly. I don't have an explanation of that, but I think it even further muddies the picture of whether you can really get arbitrarily wide rolls or they will eventually break up on just inaccessibly long timescales. That's it. Let me just leave the same questions on the screen. Thank you.
Appreciate it.
How one physically realizes fixed flux condition?
Yeah, so fixed flux is a limit of the boundaries conducting worse than the fluid. And fixed temperature is the opposite limit. So you can approach it, but you'll never have exactly that. Well, actually, fixed flux heating is easy, right? You just put heaters of a certain power along a boundary. Fixed flux cooling is a little more complicated.
Very quickly, Edgar.
Is there an analog of windy convection in 3D corresponding to a vertical vorticity model?
If you want to see something as strong as windy convection in 3D to the point that it prohibits structures from making it straight across the layer, you need some horizontal anisotropy like rotation, and this has been done.
Okay, Pat, very quickly.
Yeah, so could you comment on the ratio of the energy in the wind to the buoyancy, the convection in windy convection?
Yeah, the energy in the wind is much, much higher than the vertical energy.
Okay, let's thank David again.
Thanks.